All right, you are about to take the electricity basics quiz, and this is going to be video one of at least two, maybe even three. So when I made the quiz, here was what I was thinking. I've got some concepts with some specific terms and ideas to go with those general concepts. So this quiz is 6 questions long. Each of these 6 ideas here has one question, and I'm not going to pay too much attention to this concept right here because the question on the quiz, the answer is in the question. It's one of those where you have to read the question and think about it to get it right. So it's not something that I'm just going to tell you in a lecture. So when you guys think of electricity, what do you think of? You probably think right away of phone chargers, because freshmen are always freaking out about having chargers. And yeah, you need electricity to run your charger. Maybe some of you think about your gaming system, or maybe some of you think about, gosh, my household life, it really wouldn't exist the way that I like it if we didn't have electricity. You know, you want to do some laundry, you want to cook some food or whatever. So to understand electricity, we need to start off with electric fields. And electric fields we talked about way back in the forces quiz. You will remember that an electric field, electricity is one of those non-contact or no-touch forces. So maybe that makes you remember things that have been pushed into your brain over the years, like opposites attract and likes repel. Hopefully you have the question, well, why? Why does something positive repel something positive? And the answer is, we don't know. That's not very satisfying, I realize, but in science, you know, we don't have all the answers. We're always working on them. One thing we do know is we do know how positives act. We can describe that attraction and repulsion very well. We just don't know the reason why. You know, nobody has any idea of what the electron has that the proton wants. We're just not sure. So we imagine that these charged objects, like let's say this is a proton and this is an electron, we imagine that there is this area extending outward around these charged objects, and it can affect anything in the neighborhood. And the closer they are, the more the effect is. So we imagine these lines coming out from a proton that point outward. There's no special reason we picked outward for the proton and inward for the electron, but that's the way we draw them. So you can imagine that if an arrow were to point outward from a proton, it could point directly at an electron. So this is how we represent attraction. And what would happen if you put 2 protons by each other? Here's one and here's one. Well, they both have these arrows pointing out in all directions. But what about the arrows that would point toward the other proton? What would happen is they would deflect from each other. They would go in opposite ways. So if you had these arrows coming out from each proton, you'd have this kind of area in between, kind of this no man's land here. And that is how we describe repulsion. They repel each other. So I can't go a lot more in depth than this because number one, the math gets a little too complex, and number two, that's what's not on this quiz. So now I want to talk about the world's thinnest wire. Where is that at? Here it is. So I drew this wire here. It's the thinnest wire imaginable. It's 1, 2, 3, 4, 5, 6. It's 7 copper atoms. And why do we use copper to make wire? Well, not just because it's malleable and such. We make it out of copper because copper is a good conductor. What makes it a good conductor? Copper atoms have 29 protons and 29 electrons if they're neutral, but 2 of those 29 electrons are held very loosely. So I'm going to add 2 electrons to each of these really quickly here. And these 2 electrons are held loosely. And that means that electron is pretty free to move. This electron could jump over to this atom for a while, or maybe over to this atom for a while. You might even hear people say that the electrons, these outer electrons in these copper atoms, they're floating around in a sea of electrons. That's something you might hear somewhere along the line. So let me write down a couple definitions here while I'm thinking about it. So conductors hold their electrons loosely, like this wire over here. And insulators are the opposite. They hold their electrons, their outer electrons are held tightly. And there's lots of examples of each. We've got this copper wire here. Examples of insulators are like plastic or glass. There's lots of examples of conductors and insulators. So what would happen if you took an electron from somewhere else, right here, and you pushed it into this wire? Well, we just learned that likes repel. Well, you already knew that, most likely. But if you put in a negative in this end, all these other negatives are like, hey, get away from me, I can't stand you. What's going to happen then is you're going to have an electron that wants to come shooting out of this end of the wire. And that, ladies and gentlemen, is what we call current. Okay, so in my example here, current was made of moving electrons, and that's where most of us experience electricity. But it doesn't have to be just moving negatives. If you're talking about a chemical battery, you could also be talking about moving positive charges, and I'll get to that in a second. So I'm over 6 minutes. I'd like to finish this video up around 8, so I better hurry. So in this chemical battery, imagine this is a car battery, there's a liquid in here, and inside this liquid there is a chemical change going on. And the chemical change that happens produces electrons that head this way, and they move through the wire. I didn't draw my wire atom by atom right here. And it produces positive charges that head this way. Now, the positive charges inside the liquid battery, they can move. So inside of a liquid battery, positives can move. Let me write that. So in a liquid battery, both positive and negative charges can move. Remember, up here with my copper wire, only the electrons can move, not the protons. If the nuclei could move, then if you had electricity in a wire, you'd actually feel the wire moving, and that does not happen. It's just the negatives moving through a wire. So what happens? These electrons, they move through the wire, and when they get to the filament, they try to crowd through this tiny little fine wire here, and that generates a lot of heat, and the light bulb lights up. And then the electrons work their way back into the battery, and in the meantime, lighting up the light bulb has cost them some of their energy, so when these electrons get back to the battery, they have a little bit less energy than they had going in. So this is a good time to introduce the idea of a circuit. If there is a path for the electricity to flow through, then we say the circuit is closed. Most people say it's on. And if there's no path for the current to flow, like if I erase this wire right here, then now there's no pathway for the electrons. We would say that that circuit is off, or it's an open circuit. So batteries make electricity flow in one direction. And so do things like solar panels. So I'm over 8 minutes. I better stop here on video 1.